Hello everyone, welcome to the video lecture on gas mixture and air conditioning chapter. So today we are going to solve a math problem based on the cooling and dehumidification. So in theory class we learn about that we can do several combination in air conditioning system to create the human comfort, right? So basically this problem it's we are going to solve here. It's asking us for you know we have to create the cooling environment as well as we have to reduce the humidity. So let's take a look on this problem. So in this problem it's basically telling us that this is a duct and this duct has the diameter is 40 centimeter, right? And then through this duct 1 atmospheric pressure and 32 degrees Celsius and 70% relative humidity air is coming, right? So this is the incoming air. I would say it's a fresh air, and that fresh air incoming condition is here, and the rate of the flow rate is 120 meter per minute, right? So it's basically, and then it is the velocity 100 is 20 meter per minute. We have to convert it in meter per second later on, anyway. And then the air is cooled by passing it over a cooling coil. So this is a cooling coil, and once the air is passing through this cooling coil or outside of this cooling coil, you can see that temperature is decreasing. So 32 to it's coming to the 20 degrees C, and it's becoming saturated, right? Then it is asking us several things. So water experienced at the temperature rise 6 degrees Celsius. So when it's cooling, the fresh water or water is circulating through this cooling channel, right, or the cooling coil, and then temperature is rising by 6 degrees C. So basically it is asking us the rate of the heat transfer, right? What is the rate of heat transfer or heat absorption here happening here, QL, and then the mass flow rate of the water, and as well as the exit velocity of the air stream. So we know that V1, they are asking us the V2. So let's take a look on this problem, how we can solve it. So first thing I would like to get here, it's that the pressure, okay, with respect to the 32 degrees Celsius. So if we look from the table solution, and this is not with a refrigerant, this is with the water. The refrigerant or the working fluid is here, is the water. So we will use the saturated water table, right? So from table A4, we have at 30 degrees C, T1 equals to 32 degrees Celsius. The saturation pressure is the pressure P sat, right? P saturation pressure equals to basically 4.76 kilopascal, right? So if we look at from this appendix table A4, then with respect to this 32 degrees Celsius, we will get the saturated pressure. Why I'm asking for saturated pressure? We want to know that how much is the with respect to the 70% humidity, how much is this saturation pressure. However, we have like atmospheric pressure here, but we want to know that how much is the saturated pressure, or how much is the pressure of the vapor, right, or moisture content within that air. So that's why we are getting the saturated pressure. Then we would like to determine the saturation temperature, and from the last class, theory class, we know that whatever is the saturation temperature, that's also called the dew point temperature, okay? And that dew point temperature or saturation temperature with temperature at T equals to so I think I would like to do one more thing here. Let's take a look at the the vapor pressure. So how much is the vapor pressure? So vapor pressure, we know that vapor pressure formula, basically vapor pressure PV equals to relative humidity times the PG, right, or the saturated pressure. This is also PG. So that means we have PV equals to have the relative humidity is 70%, which is 0.7 times PG, which is equals to 4.76, right? So we have the vapor pressure PV equals to 3.332 kilo pascal. So now we know that vapor pressure, right? With respect to this vapor pressure, we would like to get the dew point temperature as or the saturated temperature, right, which is equals to 25.8 degree Celsius from A4. Okay, with respect to this pressure, then how much is the dew point temperature or the saturated temperature? Now we got 25.8 degrees Celsius for dew point temperature. However, our case, the T2 temperature or the temperature at the exit, which is got 20 degrees Celsius, so that is less than this dew point temperature. So T2 is less than dew point temperature, right? So some of the moisture in the air will be condensate. Therefore, some of the moisture will get condensate, will condense. Okay, so now that means that omega 2 will be less than omega 1. Okay, so with this relation, let's take a look in the from the psychrometric chart at state 1 or at the inlet condition, right? At state 1, what are the things we know? So at state 1, we know that temperature equals to 32 degrees Celsius. The saturated temperature is equals to the saturated temperature is equals to 25.8 degrees Celsius, 25.8 degrees Celsius. So this is dry bulb. Okay, so with respect to the dry bulb temperature as well as the humidity is 70%, 70%, then we will get from the A31, which is the psychrometric chart, right? Psychrometric chart, we'll get the enthalpy, right? Enthalpy is 86.35 kilojoule per kg. I already got all this information, right? And then we have specific relative, this is the specific humidity omega, which is 0.02114 kg per kg. Okay, please make sure that you convert it into gram to the kg, right? So it would be kg per kg. And then the velocity, or sorry, excuse me, the specific specific volume, which is 0.8939 meter cube per. Okay, so and then from there we can basically we know this information. Now let's move it to the state 2. Okay, at state, so in state 2 we have already the temperature T2 equals to 20 degrees Celsius, right? And then in state 2, what are the informations we have? (22 degrees Celsius), and then omega 1 and state 2, the relative humidity. In state 2 we have saturated, it becomes saturated, right, in the saturated line. So at 20 degrees C in saturated line, we will get basically, if this is your psychrometric chart, this will represent the saturated line, right? So for example, if this is let's say 10 degrees Celsius, 20 degrees Celsius, 30 degrees Celsius, then you go all the way up to this point. Then here you should get the enthalpy like this, you should get the omega 2 right here, right? And this is the saturated, means that it's 100% specific relative humidity, and then specific humidity you should get in this line, right? And then also you should get um, the specific volume. So that's how we get with respect to 20 degrees C and saturated saturated line. Okay, we get all this information, which is H2 equals to 57.43 kilojoule per kg, and then excuse me, omega 2 equals to, we have 0.02114 kg per kg, and we have specific volume at state 2 0.8501 meter cube per kg. Okay, so now we have all this information, and also we have H F, or H liquid at 20 degrees Celsius, which is 83.91 kilojoule per kg. Okay, so we have all this information, and we got this one from the table A4. Okay, so because it's a saturated liquid, so to get the saturated liquid, we use this table A4 to get this enthalpy. Okay, now we know this formula, right? So basically the B1 equals to V1 times A1 equals to B1 times pi times T square divided by 4, right? So we have the V1 120 meter per minute, right, times the pi times D square, which is 40 centimeters, so it would be 0.4 meter divided by 4, right, square. So in that way we can determine that the volume, or sorry, the velocity flow rate equals to 15.08 meter cube per minute. However, if we want to do the mass flow, right, mass flow MA equals to V1 divided by V equals to 15.08 divided by, this is specific volume. Okay, so this is 0.8939, so it would be 16.87 kg per minute, right? So basically this is the mass flow we got, number A, and then they're asking us the other thing, which is, so this is the mass flow. So now if we do the water mass balance, right, if we do the water mass balance, which is summation of mass of water at inlet, right, equals to summation of mass of water at outlet, right? So this is nothing but mass of air times omega 1 equals to ma2 omega 2 plus m times omega, right? So basically if we do this balancing, then we'll get mass of water, right, equals to ma times omega 1 minus omega 2, right? So from here, if we solve this, then we'll get mass of water equals to we know all of this one, we know ma, we know that omega 1 omega 2, if we plug in all this information, we'll get 0.1086 kg per minute. Okay, now let's do the energy balance, right? So if we do the energy balance, I know it's a lot of an equation we are going to use, but we have to determine step by step. So first we determine that mass flow of air, now mass flow of condensate or the water, right? Now we have to do the energy balance, which is the air and water, right? So mass of enthalpy times mass, energy balance, input equals to mass of exit times enthalpy of exit plus q out. Okay, so basically the q out equals to mass of air input h1, right? Or at the input, minus that exit mass of air times h2 plus mass of water times h2 water, right? We know all of this information. So from here we know that q out equals to 16.87 times mass 16.87 times 86.35 minus 57.43 minus 0.1086 times 83.91, right? So we'll get q out equals to, if we solve this, then we'll get the q out equals to 478.7 kilojoule per minute, right? Kilojoule per minute. Now this is the q out, and then the cooling water number B, which is asking us that q cooling equals to mass of cooling water times the enthalpy, right? Times the enthalpy, which is mass enthalpy change, delta H. Okay, so mass of cooling water times Cp times delta T, and we know that instead of H we can write Cp times delta T. Okay, so from here we know that Q cooling. So if we want to calculate this one, mass of cooling water, which is equals to Q divided by Cp times delta T. Okay, so mass equals to Q, we just got 478.7, right? And Cp we know that 4.18, right, for water. And then temperature difference was 6 degrees Celsius, because if you look at it here, the temperature difference, right, T plus 6 degrees, so T minus T plus 6, meaning that it's 6 degree Celsius difference, right? So that's why we used the temperature difference is 6 degrees Celsius only. Okay, so here, here we got 6 degrees Celsius. So if we plug in all this information, then we'll get the mass of cooling water, right, which is 19.09 kg per minute. So cooling water. So this is one answer. And then last one, asking us to determine that exit velocity, right? So we know that exit like the constant mass flow, right, ma1 equals to ma2, right, at the inlet and outlet. So that means we can write this formula, b1a1 divided by specific volume equals to v2 a2 to be capital A2 divided by specific volume 2. We know pretty much all of this information except v2. So velocity at exit point 2, so it would be v2 equals to v1 times specific volume 2 divided by specific volume 1 times a1 divided by a2. It's the same volume, same area, right? So it would be like this. So velocity at point 2 equals to nothing but 0.8501 divided by 0.8939 times the velocity, which is 120 meter per minute. So the p2 equals to would be 114 meter per minute. So in the last class we solved a problem and we saw that exit velocity is decreasing because of the moisture content and the pipe loss, right? So that's what is happening here, same here. So exit velocity is less than compared to the inlet velocity. So that's all about this math problem, right? So we saw that basically if we do the, in fact in the previous problem we are doing the similar thing, but even if in this problem if we increase the humidity, that means if we increase the moisture content, then velocity will decrease, and it doesn't matter whether we are heating or cooling, basically the velocity is decreasing at the exit. Okay, so that's all about this problem. Thanks for watching this video, and I think that's all about this problem, and this is the end of the semester. Thank you everyone for joining me in this class, and I wish you all the best for rest of the semester.